Welcome everyone to our talk. There have been a few other DevOps exploitation style talks throughout the day, so I think you guys will be pretty familiar with the topic at this point. We're going to be attacking GitHub action workflow files from open source repositories. The names on screen, me, David, Rohan, and Andrei is not here, but also one of the guys that helped build this tool that we are going to talk about. So first, who are we? We're from Whirly Labs, Cape Town-based consultancy, security consultancy company, but also we develop custom code analysis solutions. So what is that? Any kind of product or tool that helps you explore or hack a program. Usually our in-house consultants need a tool for a job that doesn't exist, and we'll create it. Last time we were here, we spoke about creating a tool for mining Java deserialization vulnerabilities from Maven. You know, large scale, just pulling these guys, analyzing the code. When a warning comes up, look at it, create a POC, and then we showed an exploit, which was quite cool. So this time it's not Java, it is a bit of JavaScript actually. So how do we, or what is a GitHub action expression injection, and how do we automate the large-scale mining of this? Well, if you don't know what GitHub Actions is, it's a CI/CD service. What is a CI/CD service? Basically automating anything that comes as a reaction of an event on your repository. So you make an issue, a pull request, you can write some code that actually reacts and does something based on that. Specifically into GitHub, that's the topic, the GitHub one, and a lot of the logic of this is defined in workflow files. It's specifically quite generous on a free tier. Once you lock your code behind a private wall, it asks you to get your credit card out before you get some computation. So yeah, you get quite a lot for your free open source repositories. An example of something you can do is on a pull request, it goes through a workflow file, and maybe you can look at an issue title or something, and then push a notification based on maybe a Slack team that should be responding. There's a lot of logic you can do, but what's important is that you can look at the branch name, the issue details, pull request details, a commit hash, and yeah, there's a lot of automation you can do. But a lot of these fields are actually attacker controlled. You can put code in an issue title, and if you don't handle it properly, you get code execution on the actions runner. So basically the computer that executes the code for that job. It's called an expression injection. Familiar faces, I've covered this not too long ago. So what are we doing? Well, we're diving deep into this topic and again, automating it. There is related work that does try to scan for these things, but a lot of them are linters, basically a little bit surface level. And what are the shortcomings of that? And how do we deploy a bit more of an advanced scanner on a large scale? So let's show an example of an expression injection. The run command is basically where your shell interpreter starts, so you can write a shell script there. And in red on the right, you will see a event pull request title. So that's a title of a pull request, and that $ with the fancy brackets, that's interpolation. So it means that anything come out of that will not only be accessed, but also be interpreted possibly as code. So in this example, you could semicolon and then write some arbitrary bash script, send some tokens to attacker.com, and that's pretty bad. Your secret's compromised, yeah, that's pretty bad. This also explores the JavaScript world, so you can have an external action. And what that looks like is you have the little, on the top right, users noob / trust me bro at v1 that references some kind of other Git repository that has a index.js or something, and that looks like that, where you have some function that uses the actions core to get an input, and it can go anywhere in JavaScript code, in this case exec, so that's code execution, but now not bash script, it is JavaScript. There could also be Docker files, etc. But it's not, sometimes you'll actually come across code that looks like this, and you can't just trust anyone's action. So what is the impact of an expression injection? Well, You can push code to protected branches. The GitHub token can have write permissions that can allow you to modify code during release pipelines. If you steal secrets, you can have privileges on systems that those secrets are for. So pretty bad, I think, is the summary of that. And really what the inspiration for us was that a cousin project of ours, open source tool that we maintain that uses that tool, they got exploited one day. They woke up to a random account called White Hat Hacker pushing to main directly with a commit title that says fixes action injection. So that's pretty wild. They were running around like headless chickens, and we were having a little bit of a giggle. It could have been a lot worse. So they are actually a security-oriented company, and for that to happen is very embarrassing. And the White Hat Hacker, that title isn't really an account. It's just they use the exploit to make some made-up account, sort of the commit author and stuff can just be specified. But that was really cool, and we wanted to know, how can we get in on that action? So how difficult is it to statically verify action workflow files that we can say that this injection exists and is exploitable, and scrape this from the whole of GitHub? Open source repositories are just there, so surely we can just download them and automate them and churn them and maybe see what comes up. And as is the case with these kinds of tools, there are false positives. Sometimes we'll say there's something and it's not really. So how do we minimize the human in the loop? And this is another candidate for the zero-day machine. So this is some early labs law. One day we'll have enough tools to just mine all the 0 days as they come out. So keep that in mind. So let's look at some related work. So you get action lint. So it's some YAML parsing matching some patterns and says if something looks pretty sus. Octoscan extends that, adds a bit more security rules instead of just the sort of best practice rules of action lint. And your friends, semgrep and CodeQL, the usual suspects, have rules for these kinds of things. They're really fast and easy to use to write rules for, and they're mostly designed for the obvious cases, the inline injections, like the earlier examples I showed, where there's pretty much interpolation right at the point where it's bad. But when you look at cases where attacker-controlled data goes into an external action, it just says, I don't know, this looks pretty bad, you should check it out, but I don't know what to do anymore. So what we decided to do was to add a way to pull those actions and analyze them on demand and put them back into the analysis. So the theme of going beyond the boundaries, that's where it is. So let's revisit this JavaScript example. Sometimes I call it a plugin, sometimes I call it external action, but related tools will just say, you've put something, the GitHub event head commit message, in an input to some external action. You probably shouldn't do that. You should probably sanitize that and call it a day. But there's a lot of room to improve on that. So we created a tool called Action Attack. Basically, it'll scrape repositories that have A, workflow files, B, have interpolated attacker control variables in those workflow files, and it will then pull that repo from the GitHub search API, determine if the expression injection actually occurs, or can it occur via some mutation or transformation in an external action, or if that external action allows attackers to define the input to some kind of vulnerable or dangerous sync, like a file write or something like that. So here's the big workflow. We will revisit this image a few times, and we'll go through it step by step. But top left is stage 1, scrape and queue candidate repositories for scanning. So that long list on the right over there, that is pretty much everything you have to watch out for. This are the interpolated values that are attacker controlled. And the GitHub API, it's pretty limited if you're using it for free, but you have to kind of give your token, and there's rate limits and all that kind of stuff. So you can't even limit the size of the repository that hits. So it'll give you the first 1,000 results of when this occurs, and you just have to live with it. So to maximize out the diversity of results, we will just give one of those syncs with the specification that they have to be workflow files. It has to be occur in a workflow file, and the language of the code has to be YAML. And so we just run that in the background, boom, boom, just in a database, here are the repositories that we should scan. Our vulnerability database now has a bunch of unscanned repositories. Now let us analyze them. So we have a YAML parser. One logic we have to check for is not all actions are vulnerable. So specifically, they have to have certain triggers. So if someone opens a pull request, if someone opens an issue, someone maybe pushes, then that is a candidate case for this to be exploitable. And the next one will to be determine if either a with command or a run command has interpolated attacker control variable in it. For example, it doesn't have to be interpolated. It could be assigned to an environment variable, and then it won't be interpreted as code, but more on that later. So initially, we tried Octoscan to minimize the effort of creating a zero-day machine, but a lot of false positives. Again, as a linter, there's not that much if checks and logic, and especially on big repositories, you get millions of results, and they're nearly exploitable, but there are a lot of reasons why it isn't actually exploitable in practice. So more on the strategy is that we then also had to determine if there is an external action. So if there's no direct injection, but there are external actions referenced, then let's register them, put them into vulnerability database as more repositories to scan, and push that repo aside for now and first scan its dependents, which are these workflow files, these actions that could be, for example, JavaScript. So that I described was queuing an action for scanning. As we've just found the action, we queued for scanning. And now let us analyze any queued actions. So yeah, pretty much, is there something to scan that is an action? Then continue. But we only handle JavaScript for now. There are other languages, like you can do it in Docker or another workflow file or bash script. Now I'm going to describe the data flow analysis. So that's just a term for tracking data. Does data at one point reach another point? And when it comes to the JavaScript, you have the way to take an input is the get input argument, and then the kind of syncs that are dangerous we're looking for, like exec, read file, write file, etc. And we just need to know some string value that goes through get input. So that would define the input. And does it define the data that goes to any of those guys? Because that's pretty bad. It's a may analysis, so like data may define that sync, but rather be safer than sorry. So there's a little bit of imprecision, but it is hopefully already minimized by all the validation we do on the YAML file. So here's an example revisited. So you can see the require file at the top is assigned to core, which is called get input, and the source value is user commit, and it defines some value that goes into exec. And as we can see over here, we have the user commit take the interpolated attacker control data, so they could define JavaScript to then execute on that, which isn't immediately obvious unless you've actually audited the action. Another way that the action could propagate attacker-controlled data is by sending it back into the action. So actions can define outputs. And another data flow analysis that we perform is to check, in case now is the sink defining an output. So the output would look something like steps, and then the ID of the step, outputs, and then the output name. And if that is interpolated, that is another attacker-controlled value, which is what a lot of the linters say. The linters would say that anything that looks like that is always going to be bad, but we want to sort of minimize that false positive rate. So after this data flow analysis, we get a whole new set of sinks that says, yeah, if attacker goes into that input, attacker comes out again. So here's another example. We can see, again, source value, user commit, and then undergo some kind of processing or whatever, but then it goes to the output using core.setOutput. And we can see on the left that if in this step, my action it takes that attacker-controlled action. We can then assume that this is also attacker-controlled, and if it goes into a sink, they also have RCE there, or expression injection there. So, that is some of the novelty, and the sort of pushing the edge of what other tools don't do. Sneak came up as one of the actions that actually have this vulnerability of doing bad stuff. So specifically on the inputs, the sneak version and the input OS are just interpolated values that the attacker controls. So it's not very regular that for an input you would let the attacker, or like you would give a pull request title to define a sneak version. But it is an interesting way that to think that there were ways to mitigate this and assign this to an environment variable, but they decided not to. And it's surprising that this kind of, I don't want to necessarily careless, but it is unlikely that someone's going to misuse this, but yes, it is not best practices. And yeah, that did come up in our analysis. So you could probably trust this action, but if you gave bash script to the sneak version, it does execute, which is pretty bad. Though more likely the case is that the only thing that's going to be interpolated into that is going to be something coming from like the job matrix. But yeah, and that's kind of a theme we'll see, is that while there are a lot of ways to exploit these things in practice, yeah, attacker control variables don't always go into these inputs. So as we are open sourcing this tool, we thought we might as well make it at least look good. And Andrei made a nice little terminal GUI, and you can see all the repositories on the left, all the findings, a bit of code. So it's been a nice fun tool for you guys to check out. Hopefully it motivates you. But yeah, that's enough of the technical design of the tool. The results are going to be the sweet little thing at the end. But for now, let me hand over to Rohan, who is my security rubber ducky.
Thank you. Thank you, everyone, for coming to our talk. As David said, this is affecting CI/CD pipelines. And if anyone here uses GitHub, please raise your hand. That's quite a bit of you. So you can see GitHub is quite a popular tool. Some people might not know about it, but it's quite useful. And does anyone here use GitHub Actions? Yeah. Personally, I haven't used it until now. I'm glad I didn't. I'm just going to try and go to the next slide. Okay, cool. Yeah, so this sounds pretty bad. Remote code execution, even though we've seen it a few times and we've gotten kind of desensitized to it, especially from all the good research coming out of Wally Labs. We should still be quite careful about this, because being able to execute code on a machine, even though it's just a runner in this case, the runners don't have to run on GitHub machines. You can have a runner running on your own personal machine. And this can be good and bad for some, in certain cases. If you're running this code and you get code execution on a GitHub runner, a GitHub hosted runner, you most likely wouldn't have any of your personal stuff on that machine, though you do have your GitHub token. You also wouldn't be able to see the output of the program if you have the code running on your own personal machine. So for GitHub, the runner shows the log, or the output. The output of the runner is shown on the GitHub interface. But if you have the code running on your own machine, or the runner running on your own machine, nobody would really be able to see it unless you configured it in that way. So why haven't you seen a ton of stuff about everybody's GitHub repos being owned, or about that white hat hacker that fixed our sister company's repo? Well, by default, at least from now, GitHub has a few configuration security configurations in place. For example, any organization made after or in 2022, their repos, newly created repos, their tokens are set to read only by default. So you would have to purposefully go into the token settings and say, I want this GitHub token to be able to edit I want the GitHub token to be able to edit files in the repo. Otherwise, it would just have read access, so it would be able to see the titles or the pull requests coming in, but it wouldn't actually be able to make any modifications. And also, GitHub Security Lab does their rounds. They go around checking some known vulnerabilities. They probably have their own scanners as well. So yeah, you have your permissions. You can you can set what you would like your actions to be able to do and what you'd like your tokens to be able to affect. As you can see, they have some options. Is that laser? Oh, okay, cool. The disable actions shows that even if somebody accidentally in the repo makes a push and says that, hey, I'm going to create an action, whoever owns the repo can say, no, you can't. And workflow permissions, as I said just now, by default now, the GitHub token that's created when the workflow runs only has read permissions, but before 2022, it used to be the default the default used to be read and write permissions, which sounds extremely safe. And also, this is quite a dangerous one here. If you have this checkbox checked, you should probably go into your GitHub repo and change it right now during this talk. So this basically means that if somebody forks your repo, if your repo is public, any changes, any actions running on the forked repos can affect the base repo. So it doesn't even matter if there are some configuration settings in the base repo that prevent this from running from working, because it will affect the base repo no matter what. Yeah, and now comes the most boring part, actually fixing the vulnerability. Please don't do this. Setting your permissions per job is recommended. So under your actions file, you have this permissions keyword that you can use, and you can set permissions for a few different sections or facets in the workflow actions. And the main ones are contents. Oh, sorry. And the main ones are contents and pull requests. So the content permission, if it's set to write, allows a action, or rather the GitHub token that's created for that action, to modify the repo, which means it can create pull requests, it can create files, it has write access to the contents. And the pull requests permission, funny enough, makes perfect sense, doesn't actually allow you to create pull requests. So if you want to stop somebody from making pull requests, setting pull requests to deny doesn't actually stop anyone from making pull requests. You have to set the contents permission to read or none. The pull requests permission actually only lets you control whether someone can label or comment, or sorry, if the action can label or comment on the on an issue, or sorry, on a pull request. So, sorry, my mouth is getting really dry. So these are the global permissions usually set for all of the workflows in a repository, and this would be per workflow. So workflows are usually split into into different workflow files that contain related jobs. So in a workflow file, you have a job, or you have multiple jobs, and those jobs have steps. And you can set permissions per job, and that is the recommended way to do it. So this is an example from the. Are we allowed to? Are we gonna say what? No, I'm guessing because you took it out. Yeah, it's not on the screen. Okay. Oh, it's on the screen. Yeah. So this is a real-world example from the Grafana repo. It's still live. If anyone wants to go and do anything to it. So we did send them emails to fix this, but they didn't really acknowledge that. So yeah, you can take a look at the actions file, and it contains a run keyword. This is quite a nice little find. It contains a run keyword with a reference to the name of the pull request. So this action runs when a pull request is made, and specifically when the pull request name starts with release and it gets merged. So if you make the pull request name something that is a command, you can get that to run in the runner. Yeah, that's, sorry, I'm just looking at that because it's just so. Yeah, it is a little bit more difficult to exploit, since it is the title of, sorry, the href is actually not the title of the pull request. Href is the title of the branch that you create that you're going to be merging. So it's a little bit more difficult to exploit in this specific situation because branch names have character restrictions. You can't have, for example, a backslash in the name or a quote, which means it's a little bit more difficult to escape from this context, but there are ways. So the recommendations for when writing GitHub Actions: don't use run. Wherever you can, not use run, because that is just asking for trouble, and somebody later is going to come and make a modification to the run file, which makes it vulnerable. But there are other ways to do this. For example, if you want a action that labels a pull request or an issue, instead of having a run keyword in your action, you can use something like a pre-made action, a JavaScript action that somebody has created, not because somebody else is a better programmer than you, because we all know that we are the best programmers, but rather because if you have your if you use the run keyword and you are interpolating any name that the user can control, then they can essentially inject anything into that unless you use environment variables. And that's the next thing. Use environment variables for user-controlled strings. So if you're going to interpolate the name of a pull request or an issue or anything that a user can control, put it into an environment variable. And what this does is it stops GitHub from treating that as a command, and it just treats that value as a string. You should set your settings to require approval for outside collaborators. One of the settings is require approval for first-time collaborators, but that is still dangerous since someone can make a change that's actually useful, and then that pull request gets accepted. And then after that, they're like, okay, cool, now we can mess with the repo. Thank you. So something that you should definitely do is disable workflows for forks, because you don't want people to be able to control your runners from their forks. Your base repo is yours. let's keep it that way. Now, the difference between pull request and pull request trigger is a great example of GitHub's brilliant documentation for their actions. So if you haven't used actions before, one of the main ways, one of the things that you always have to set up is the action that triggers your action, the thing that triggers your action. And that is set by the on keyword. So you can choose different events that would trigger your action. For example, if someone creates an issue, an action would run. And in this case, if you want an action to run after a pull request is made, you have two options. And now if you Google, how do I get an action to run on a pull request, you might come across a tutorial that tells you to use pull request trigger. And if you did that, anyone that forks your repository and runs an action will have run access on your repository. So this event means that that action that runs on someone else's repo will have access to your repo secrets and a bunch of other nice, fun little party tricks. Permissions should be set to none for as far as possible, as the slide says. Yeah, as you can see, I prepared very well for this talk. You want your permissions to be set as low as possible, like in any situation. I think if you are setting some permissions on actions globally, you should make sure that any actions that do have the run keyword also are configured specifically or configured individually, because those would be the most targeted. Okay. Yeah, back to Dave. Thank you.
Okay, so I know it's been pretty academic, pretty nerdy, and pretty lectury, but let's actually see what this imaginary tool we wrote found. So we showed some close findings, which were like, yes, it exists, but there's very limited scope into how we could exploit it. But there are more legit findings. So a 7-hour scan found 111 findings out of 17,500 repositories, which included scanning the external actions. 73% of them were true positives, i.e. they are exploitable if they didn't follow all the mitigations that Rohan spoke about. So there are some things that we can check, like the permissions, but a lot of the stuff that are user settings are sort of a bit more tricky to actually validate covertly. Like we would have to make a pull request, for example, and then it would say you're blocked until someone approves you, and then you're like sitting there with some huge binary script injection in your issue title, and you're like, okay, time to close that quickly. So yeah, depends on the mitigations, but from this, about 65% precision. A lot of the false positives came from JavaScript plugins. So we did correctly track a input to an output, but there was some kind of sanitation that we didn't validate at the time of the analysis. So like stringify will pretty much transform your any kind of script or injection to something pretty unusable, but that can be accounted for. So in the latest version on master, we have accounted for some of the sanitizers, so that improves our precision to closer to 80%. What is left over is stuff that is like maybe they'll actually check your variable for certain commands, codes in the bash script that is a little bit non-deterministic, quite difficult to actually validate without running the program. But that's pretty good. I think for all you bounty hunters out there, yeah, give it a run. Here's one that looked pretty good. One of the biggest projects that came up with the findings, 38,000 stars. Again, a head ref, so pretty tricky, but you have control, you have access to that. And on the right is our tool's report. So that gives you the line number, where something's been used. It actually might be the wrong screenshot, but in any case, the vulnerabilities on the left, on the right, I think is the same repo, but a different vulnerability that actually uses the pull request body. So yeah, that is probably the more impressive legit finding we found. And some future work is to prioritize active projects. A lot of those findings were smaller projects, dormant projects, maybe something that we don't really care to exploit. Lots of things that you could just make like an issue and you can, hello world, their action. Maybe support some external types and refine filtering, try to covertly detect some of these permissions, these mitigations as fast as possible. Even during the creation of this tool, a few more things were added that we had to account for that made certain things no longer exploitable. So before the demo, we do have time for a demo, yes. Here's the tool. Go ahead, run it. All you need is a GitHub API with pretty much no permissions. It just needs to be able to use a search API and see what you can find. Because obviously, I know the hacker community respects big corporations and not showing 0 days for them. So I've left that in your hands. And with that, let me open the IDE. So this is what the project looks like, or the README thereof. Some instructions. And AutoGPT is one of those classic examples that you'll find in a lot of blogs. So let us run. This is a once-off scan. This is not the monitor that scrapes. That's a different mode. You give the repo owner the name and the commit you want to say, and then the name of your database file. It's a SQLite file. We'll be scanning and cloning. So what's happening now is basically it'll fetch from GitHub, clone the repo. If it's a big repo, it takes a bit of a while. Checks out to the commit, and then runs the scan. The scan is pretty fast if you don't need to pull any actions, because then each action is another repo to scan. And then it will store the findings in the database as unvalidated, or unvalidated by a user. So there it's done. So then we go to review mode. So review mode will give us this little guy. So if we have multiple repositories, you'll see them on the left. You can use the arrow keys to go between these screens. The body is, you need internet for this. The body of the code is actually pulled from GitHub. And it'll say, what's wrong. In this case, there is a pull request head ref, various pull request things in a interpolated string. And then you can press yes or no to then say it's valid. So I'll say yes, you can say yes again, and then we validated all the findings that we've mined. And then a little report, let's generate that. So this will generate a little HTML report of everything that you've found to be valid. So I believe it's this guy. And yeah, the stuff that you validated will come here, and then you can show in GitHub. And it'll also highlight the line for you to see. So pretty fun, pretty cool. Yeah, here's another hit, I guess. Yet another repository we've pointed out on to an audience of cybersecurity professionals. But this one is an interesting example because this is an example where they do put it through an environment variable, but then they again put it in a interpolated string. So then it would have been safe if it was just a $sign and accessed like an environment variable, but it's been, and this is actually mentioned in the GitHub documentation, if you put the interpolation around it, it becomes interpreted as code again, so then it's exploitable. So this we call an aliased injection. So that's another kind of injection that the tool detects. So yeah, that is our talk. Any questions? Yeah. So everything is in the SQLite database, which I think would be the best. Yeah. So then, yeah, just SQLite, findings is valid validated, and then you can take all the properties. It also includes the details of the actions that it uses. There is like a foreign key connection, and then you can say it is vulnerable because of these actions that have this vulnerability, etc. Yeah, and then generate your own reports. I would say the HTML is more of just a proof of concept kind of, here's a nice little report. Yeah, sure.
So you can localize the stage to, let's say, one specific repo or like specific report within like maybe like a company features, like a specific account.
So the scan command will basically run the monitor as if it just has one repository to scan. So in a way, that is the functionality it does. The way the code happens, if you want to do something like that, you can also insert the repos into the database, and then the background thread will just pick it up. If you say repo commit unscanned equals, well, is scanned equals false, then the process will pick it up, scan the job, and then the findings will land in your database again. Yeah. I'll probably go on holiday. It is December, but in Jan, if you open up some issues, I'd be happy to take a look and get them sorted. Maybe even if address some of the future work. I think yeah, this is our first big open source project as the company, so it'd be great to see some tooling for you guys to use. Cool. Thanks.
Across the attack surface, scattered products and siloed views create blind spots that feel unstoppable. The deadliest risks are in these gaps, where attackers move in. It's time to unify fragmented snapshots into one all-seeing view of risk and unleash a platform born with one intention: isolate and eradicate your priority exposures. From IT infrastructure to cloud environments to critical infrastructure and everywhere in between. This is Tenable. Your exposure ends here.